Hello everyone, I am Omar Gupta, a PhD scholar at IIT Kanpur. Today we will discuss about the big five of fundamentals of supersonic and hypersonic flow. Due to some issues, uh, the previous lecture which was uploaded was removed, so new lecture is being uploaded. So we'll discuss some problem related to big five, and we will also discuss some theory. The first problem is if a product Nk, where N equal to number density and K equal to Boltzmann constant of a gas has a value 320 joule per meter cube Kelvin and molecular weight of the gas is 32 kg per kilomole. Its density R is given 8314 joule per kilomole Kelvin. So before solving this problem, we'll first discuss some theory. So in this problem itself, what is this product Nk is given. So where N is the number density. What is the number density? Number density is nothing but number of particles upon volume of the gas. And K is the Boltzmann constant. So product of these two is given. And we know the molecular weight of the gas, which is 32 per kilomole, kg per kilomole. So we need to find its density. We'll see some theory first. So we'll see what is the perfect gas. So what is perfect gas? Perfect gas is gas in which intermolecular forces are neglected. So generally between the two molecules of the gas there is some intermolecular force. So for the perfect gas we neglect all these kind of force. And second thing is that if you see that one molecule occupy a space, we also neglect that space occupied by the molecule also. So like imagine that molecule is a point, it is not occupying any space, or molecule does not have any volume. So the perfect equation is given by PV equal to mRT. Here P is the pressure, M is the mass, V is the volume, and T is the temperature. And R is the specific gas constant. Notice that this R is specific gas constant, which will depend upon the type of gas, and it is equal to R bar upon M bar. Here R bar is universal gas constant. It is constant for all gases, which is equal to 8314 joule per mole kilomole Kelvin, which is given in the problem also. This in the problem also this is R bar, which we are using because it is very confusing which will be R and which will be R bar. And what is M bar? M bar is the molecular weight. For this case also molecular weight is K. So here I have written the value of R bar, which is nothing but 8314 joule per kilomole Kelvin, which is for all gases. And R value will depend on the gas. So for the air, you can remember this value, which is 287 joule per kg Kelvin. Now we will write different forms of perfect gas equation. Another form is PV equal to RT, where V is for specific value. And what is specific value? Volume. It is nothing but volume upon mass. So we know that PV equal to mRT. So if we take m on the left hand side, we get PV upon m equal to RT. And V upon m is what? Specific value. So PV equal to RT. We get this one. Now we see another form, this which is in terms of density. So density is equal to 1 upon V, 1 upon specific volume. Or you can see that mass upon volume. So we already have our form PV equal to RT, so we directly use that. So if V will go to the right hand side, it will become P equal to 1 upon VRT, where 1 upon V is equal to rho. So PV equal to RT. Here one thing to notice, everywhere it is specific gas constant. Currently there is no universal gas constant. Now there is another form, PV equal to N RT. We will use N bar. So we can distinguish N bar is number of moles. So first thing to how to derive it, we know that R equal to R bar upon N bar. And R bar is universal gas constant, N bar is molecular weight. So we know the perfect equation, which is given by PV equal to nRT. If we put substitute value of R from this equation, then we get PV equal to N upon N bar here what I did, I multiply and divide by M bar. Same thing. If we divide by M, so it will become M upon M bar R into T. M bar R is what? R bar equal to M bar R. So we can write M bar R equal to R bar, and M upon M bar is what? Number of moles. Because number of moles is what? Mass upon molecular weight. So we get PV equal to N bar R bar T. Now we will see another form. P V bar equal to R T. Here V bar is molar volume, which is what? Volume upon number of moles. This also you can transform over equation, which was PV equal to N bar R bar T. If we take this N bar to left hand side, we can get P V upon N bar R T, and volume upon number of moles is what? Molar volume. We will get P V bar R T. This R is R T. Another form is P equal to C R T, where C is the concentration, and concentration is given by number of moles per unit volume, which is number of moles per unit volume, number upon V. And if you see from here, it is reverse or reciprocal of mole volume. So now now we have this equation PV equal to n bar r bar t. If we divide left hand side and right hand side by V, we will get P equal to n bar upon V r bar t. And n bar upon V equal to what? Concentration. We will get C r bar t. Now next form is PV equal to eta r t, where eta is mole mass ratio, which is, you can simply say, number of moles upon mass. So it is equal to number of moles upon mass. So if you see the previous expression, PV equal to n by r by t, if we divide both sides by n, where this V is specific volume. So in this equation, if I divide both sides by n, then it becomes P V upon n equal to n bar upon n r bar t. And this n bar upon n is what? Eta. And V upon n is what? Specific volume. So we'll get PV equal to eta r bar t. You might be thinking that why are we studying this different kind of forms of perfect gas equation, but all forms have different kind of use in different cases. Like previous problem itself, which I told, which I have not solved till now, will also use one of this form of the equation. Next form is PV equal to nkt, where n is the number of particles and k equal to Boltzmann constant. So to derive this, let's say initially we have equation PV equal to n bar r bar t. Now if we multiply and divide by n is Avogadro number, which is given by 6.022 × 10⁻93. We multiply and divide by Avogadro number. This n bar is what? Number of moles. Number of moles into Avogadro number is number of particles. So one of the definition of number of moles is number of particles upon Avogadro. So here we get n and r bar upon n. It is given by another constant, which is written as k, and it is called Boltzmann constant. So PV equal to nkt. Now another form, P equal to nkt, where n is the number of particles per unit volume. So in this equation itself, if we take this V on the right hand side, we will get P equal to n upon V kt. And n upon V is what? Number of particles per unit volume. It is also called by number density. So we get P equal to nkt. One more thing is the value of k is given by Boltzmann constant. K is Boltzmann constant. It is given as 1.38 × 10⁻23. You can also find by this r bar upon n. R bar value you know 8314, and n value is also 6.022 × 10⁻23. By dividing simply, you can get this value of k. So till now we have seen many different forms of equation of state, and these all forms of state are written in the tabular form. So in the equation you might have seen in some equation there is mass is there, and in some equation there is number of particles is there, and in some equation there is mole is there. So based on that you can say that some of the equations are written based on number of particle basis which will have k. All these kind of equations will have k in Boltzmann constant. Some are written based on mass which will have a specific gas constant, and some equations are written based on mole which have universal gas constant. So for the mole basic equation as Pv equal to mRT, Pv equal to RT, and P equal to ρRT. Mole basic equation are Pv equal to m bar r/t, Pv bar equal to r/t, P equal to c r/t, and Pv equal to beta r/t. And the particle basis equation is Pv equal to nkt and P equal to nkt. In all these equations, capital M is mass, small b is specific volume, rho is density. Capital M bar is mole, capital B bar is molar volume, C is concentration, eta is mole mass ratio, N is number density, and capital N is number of particles. P is pressure, T is temperature. R is specific gas constant, R bar is universal gas constant, and K is Boltzmann constant. Now we will solve the problem. So in this problem itself, what all are given? Product of NK is given, molecular weight is given, and R bar is given. What do you have to find? Density. So we have to find two such equation of state such that rho and nk are connected. Rho and nk are connected. Nk is only in this equation, P equal to nkt. And if we this equation is P equal to ρRT. If we equate this equation together, we will find value of rho density. How do we solve it? We have two equations, P equal to nkt, P equal to ρRT. Nk value you know 320 joule per Kelvin meter cube, capital M value, bar value, molecular weight equal to 32 kg per kilomole. Now these equations we can equate. So nkt equal to ρRT, T will cancel, so rho will be equal to nk upon R. And we know that R bar equal to R bar upon M bar. We will substitute this here. Now we put value of everything. Nk value is 320 joule per meter cube Kelvin. M bar value is 32 kg per kilomole. R bar value is 8314 joule per kilomole Kelvin. So if we solve this together, we will get 1.2317 kilojoule kg per meter cube, which is density. So which one is the correct answer? Answer is option B. Now we will see the second problem. Give free energy per mole of a gas mixture is given by H enthalpy, T temperature, S enthalpy per mole of the mixture respectively. So there are four options: A equal to h upon t plus s, B equal to ht minus s, C equal to ts plus h, option D h minus ts. So first we will see what is gift free energy. It is denoted by G, and it is nothing but it is thermodynamic state variable. State variable is a variable which depends on only on states, not on path, and it is given by G equal to h minus ts, and all these quantity are given in the per mole of the mixture. So which option is correct? Option D is correct. Now we will see another problem. The molar volume in terms of gift free energy G is given by option A minus dou G upon dou T at constant pressure, option B dou G upon dou P at constant temperature, option C dou G upon dou H at constant pressure, option D dou G upon dou S at constant temperature. What will the answer for this? If you remember the formula directly, you can directly mark it as option B, dou G upon dou T at constant temperature. If you don't remember the formula, then you would see how to derive it. So we'll start with definition of gift free energy. So how is it defined? It is something like G equal to h minus ts, and in here all the quantities are per mole of the mixture of the gas. Now we'll take the derivative of this equation. We will get dg equal to dh minus tds minus s dt. We will write everything in terms of dh. So dh equal to dg plus tds plus s dt. Now in the equation there is no volume term. We want a volume term also. So we will write this h using the definition of enthalpy. H equal to U plus P V1. Why we have taken this V1? Because everything is written in the molar parameter. So S, H, S, T all are in the per mole of the mixture. This quantity also will be mole quantity. So we'll take the derivative of this equation. We get dH equal to du plus pdv var plus v var dp var. And if you see this part du plus pdv var, it is nothing but reversible heat. So it is equal to del Q reversible. So if we write everything in terms of this, we get del Q reversible equal to dH minus v bar dp. This is second equation. Now we have two equations, first and second. But one thing is that we have to write ds also. So ds equal to ds reversible and ds irreversible, because entropy is the combination of reversible and irreversible entropy. And reversible entropy is given by del Q reversible upon T. So ds will become equal to del Q reversible upon T plus ds irreversible. So this del Q reversible, we know it is number, it is dH minus Vr dP. If substituted here, we will get dS equal to dH upon T minus Vr upon T dP plus dS irreversible. Now we multiply with this by T. We will get T dS equal to dH minus Vr dP plus T dS irreversible. Now from the equation first we get the value of dH. We substitute this dH here, which is dH equal to dG plus TdS plus FdT. We substitute in this equation. So we'll get TdS equal to dG plus TdS plus FdT, and other terms are minus Vr dP plus TdS irreversible. TdS will cancel. So we'll get dG equal to minus S dt plus Vr dP minus TdS irreversible. We took all these three terms on the left-hand side. This is the equation number 3. Now let's see for the equilibrium flow. So for the equilibrium flow, this dS irreversible will be equal to 0, because for equilibrium there is no irreversible entropy. So in that case, if you see from this equation, or normally also this G will be equal to G Pt, because all the exit variable are function of Q variable, which is referent temperature. This for equilibrium. But for chemical non-equilibrium, dS irreversible will not be 0. So what will happen? G will also depend on the number of particles of species I. So G will depend on Ni, which is number of particles of species I per molar or mole of the mixture of the gas. So if let's say there are n species, then G will depend on Et, N1, N2 to N. We are taking this number of particles because in chemical reactions only this number of particles will change, which is not constant in the equilibrium. That's why these all terms are taken together. Now we'll take the derivative of this G. We'll get dG equal to dou G upon dou Pt dP plus dou G upon dou Tp dt plus, let's say if we are taking derivative with respect to n, then it will be dou G upon dou n1 dn1. Similarly for other n, so if we combine all of those together, we get sigma I dou G upon dou ni dn. Now compare it with this equation. If we compare it, then we have to compare dP term to dP term, dt term to dP term, and other term will be this term. For dP, if we want to find B bar, then we have to compare dP term. So here dP term is dou G upon dou P at constant temperature. B bar will be equal to dou G upon dou P at constant temperature. Which is option B. Now we'll see the another problem. The entropy caused by chemical non-equilibrium is expressed by Gi is given free energy for species I, Ni is number of moles of species I, where this Ni is not number of moles, it is number of particles per mole of species I. Pi is the partial pressure of the species I, T is the mixture of the gas, P is the mixture pressure. So there are four options: A equal to -1 by T sigma I Gi dni, option B 1 upon T sigma I Pi dgi, option C 1 upon P sigma I Gi dni, and option D 1 upon T sigma I Hi dni. Here it is number of moles only, that is my mistake earlier. So what is the answer? First, see what we want to find. We want to find D. We want to find the entropy change caused by chemical non-equilibrium, which you can say ds at reverse. Now previously we are finding the D reversible only, and we are including it in the equation also. Now this third and fourth equation. This equation we are going to keep it here. This is fourth. We are comparing third and fourth. See, in the third there is dp term, ds term. Deciding whatever is there will be equal to this minus T ds. dp term is there, dt term is there. So minus T ds is also equal to sigma I dou G upon dou Ni dt. Yeah, I have written both equation again. So dg equal to dou G upon dou pt dp plus dou G upon dou Tp dt plus sigma I dou G upon dou Ni dt. And second equation is dg equal to minus S dt plus mu bar dp minus T ds and reverse one. So this dp term form, dp term form. So this term will be equal to this term. So minus T ds reverse will be equal to sigma I dou G upon dou Ni dt. Let's move equation 4. So now we let the here in the equation, this G is the gives free energy per mole of the mixture. Now let's define another term, Gi dash. So what is Gi dash? Gi dash is the gives free energy of species I per particle. So if Gi dash is the species gives free energy of species I per particle, so Ni into Gi dash will be what? gives free energy of species I, where Ni is the number of particles of species I. So what will be equal to total gives energy? It is equal to sigma I Ni Gi dash, which is nothing but Ni Gi dash Gi N1 G1 dash plus N2 G2 dash and so on to Nn Gn dash. And before this, what was the Ni? Ni was the number of particles of species I per mole of the mixture. So this is for the per mole of the mixture. Now G equal to sigma I Ni Gi dash. So here if we take the derivative of this with respect to Ni, we will get Gi dash. So dou G upon dou Ni equal to Gi dash. So here we have that dou G upon dou Ni will be equal to Gi dash. We can write it as ds irreversible equal to minus 1 upon T sigma Gi dash dni. Now this is the number of particles. We can multiply it by Na and divide by N. The number of particles per mole upon Avogadro number will be number of moles of species I. Change in number of moles of species I. Which is d by dni bar. So and any Gi dash will be equal to what? Gi was what? Gi dash was the free energy of species I per particle. If we multiply it by Na, then it will be per mole of species I. So it will be equal to Gi. So ds irreversible equal to minus 1 upon T. If you substitute this here, sigma Gi dni bar. Here everything will be bar. So answer for this problem will be minus 1 upon T sigma I Gi dni. We'll see the next problem. For an equivalent chemical reacting gas mixture comprising of 3 species, namely species 1, species 2 and species 3. The change in number of moles of species 3 can be expressed as Gi equal to the free energy of species I, dni equal to change in number of moles of species I. So there are 4 options: G1 dn2 plus G2 dn3 upon G1 plus G2. Sorry, G1 dn2 plus G2 dn1 upon G1 plus G2. Option B, G1 dn1 plus G2 dn2 upon G3. Option C, minus G1 dn1 plus G2 dn2 upon G3. Option D, minus G1 dn1 plus G2 dn2 upon G1 plus G2. So now it is going for chemically equilibrium, chemically reacting gas mixture. So till now we are finding D as irreversible. So now if let's say there is equilibrium, chemical equilibrium, then value of this DS irreversible will be equal to 0. So for the equilibrium chemical reacting gas, what will happen? This sigma GI dNi bar will be equal to 0. So let's say if it is 0, then for the 3 species system, it will be, if we expand this, it will be equal to this is also an important relation. Okay, go on to it. So if this is 0 for 3 species mixture, it will be equal to G1 dN1 plus G2 dN2 plus G3 dN3 equal to 0. Now we have to find dN3, which is equal to, we will take these two on the right hand side, and it will have dN3 equal to minus G1 dN1 plus G2 dN2 upon G3, which is equal to option C. So option C is the correct answer. Now we will see some more theory, and this time it is related to equilibrium constant. So equilibrium constant is related to equilibrium chemically reacting mixture, and it will happen only when there is equilibrium is there. Now before we have found that ds irreversible will be equal to minus 1 upon T sigma Gi dNi bar. So for chemical equilibrium, what will happen? If ds irreversible will be equal to 0. So if you take this right reaction side equal to 0, we will get sigma Gi dNi bar equal to 0. Now let's take a general chemical reaction, which is given by nu1 dash A1 plus nu2 dash A2 plus so on nu k dash AK, and it will give nu k plus 1 dash AK plus 1 plus nu k plus 2 dash AK plus 2 plus nu j dash AJ. So in this equation we can see that from index 1 to k are reactants, so total reactants are k, and index k plus 1 to j are products, so total products are j minus k. And this combined reaction, if we take everything on the left hand side to right hand side, we will get sigma I equal to 1 to j mu I ai equal to 0, where mu I can be positive or negative. So let's take an example. We have one reaction where H2 and O2 are making water, and it is formed by 2H2 plus O2, which will give 2H2. So if we take this H2 and O2 to right hand side, we can get that mu H2 will be equal to 2 because for reactant it is positive, and mu O2 equal to minus 1. Sorry, For product it is positive, mu O2 equal to -1 and mu H2 equal to -2. So let's say there is any changes happening in the number of molecules of species I. Or let's say number of moles of species I, so which will be proportional to mu I. So let's say mu I is equal to 1, so it will be proportional, change will happen in proportional to 1. If it is 2, it will double, like that. So the ratio of all this number of moles of species I is given by dn1 dn1 ratio dn2 bar plus ratio dn3 bar and so on to dng bar equal to mu1 ratio mu2 ratio to so on to mu j. Now we will introduce a new proportionality constant. So if we include a one common proportionality symbol, it can be given by d on 1 bar upon mu1 equal to d and 2 bar upon mu2 and so on equal to d and j bar upon mu2 which will equal to 0. So d and 1 bar will be equal to mu1 d z. Similarly, d and 2 bar equal to mu2 dz. D and 3 bar upon will be equal to mu3 dz. Similarly, d and j bar is equal to mu j d sub j. Or from that, or we can write d and I bar equal to mu I dz. Now, in the previous equation which we have derived for equilibrium flow, which was sigma I gi dni equal to dni bar equal to 0, we will substitute value of dni, which will give sigma I gi mu I dji equal to 0. And we know that dji is constant for all the species. Hence, dji can come out from the summation, which will be dji sigma I gi mu I equal to 0. And we will get sigma mu I gi equal to 0. This is an important relation. And this is also a condition of for chemical equilibrium. So let's say for any reaction, we know the stoichiometric coefficient of that reaction, and we know the free energy of the each species. We can find the condition of chemical Let's take this Gi equal to Hi minus Tsi, and Fi can be given as integration T reference to T Cpi dt upon T minus R bar log Pa upon P reference plus Fi reference. If we combine these two, like if we substitute this Fi here, we will get Gi equal to Hi, which is similar to before, minus T integration T reference to T Cpi dt upon T minus R bar log Pi upon P reference plus Fi reference. Now let's take this Pi equal to 1 atmosphere. Then we'll get Gi Pi equal to 1 equal to Hi minus T integration T reference to T. Here this log Pi upon P reference can be written as minus R bar log Pi minus log P reference. Now if we put P reference equal to 1, this value will be 0. So we'll get integration T reference to T Cpi dt upon T plus R bar log P plus S I, oh sorry, one mistake. We are putting value of Pi equal to 0, not P reference. Pi equal to 1, not P reference equal to 1. So this term will be 0 and minus minus will become plus. Value plus R bar log P reference plus Si reference. Now we have two equations. One is this Gi equal to this equation, and one is this Gi Pi equal to 1. So if we subtract equation 2 from equation 1, we will get Gi. Let's say we are subtracting these two equations, then on the left hand side we will get Gi minus Gi Pi equal to 1. Hi will cancel, this term is same, so it will also cancel. Fi reference is same, it will also cancel, and P reference term is also same, so it will also cancel. So what will remain is this minus minus will become plus, so it will become R bar T log Pi. So if we take this Gi Pi equal to 1 to right hand side, we will get Gi equal to Gi Pi equal to 1 plus R bar T Pi. Now we know that for the chemical reaction, for chemical equilibrium, sigma I mu I Gi equal to 0, where we can put this value Gi from this equation. So we'll get sigma mu I Gi Pi equal to 1 plus mu I R bar T log Pi equal to 0. We'll separate these two terms. So we'll get sigma I mu I Gi Pi equal to 1 equal to this R bar T is constant. So it will come out on the summation, so it will become plus R bar T sigma I mu I log Pi. Let's write this term sigma mu I Gi Pi equal to 1 equal to delta G P equal to 1. Which is nothing but sigma I mu I Gi Pi equal to 1. And it is simply the give free energy of the product minus give free energy of reactants for the all of the species evaluated at 1 atmosphere pressure. Now here like this Gp equal to 1 for product minus Gp equal to 1 for reactant. Now if we take to the right hand side, we will get delta G equal to 1 upon R bar T from here equal to minus sigma I log Pi to the power mu I. Here this mu I can go to the power of Pi, so it become log Pi to the power mu I. Now if you see sigma I log Pi to the power mu I is nothing but summation of all this log Pi to the P to the power mu I. If we write it, it will become log P1 mu1 plus log P2 mu2 plus so on Pj mu j. From the logarithm we know that log A plus log B equal to log A. So this sigma I log Pi to the power mu I will be equal to log P1 to the power mu1, P to the power mu2 and so on Pj to the power mu j, which is nothing but product of Pi mu I. So it will come equal to log I equal to 1 to j Pi mu I. And this pi I equal to 1 to j mu I mu I Pi mu I is nothing but reaction constant, equilibrium constant. So if we substitute this in this equation, we will get log pi I Pi mu I equal to minus delta G equal to 1 upon R bar T. If we remove this log, we will get pi I Pi mu I equal to e to the power minus delta G equal to 1 upon R bar T, which is equal to Kp, equilibrium constant. Any doubt till now? If you have doubt after watching my lecture, you can comment also. If possible, I will try to reply it. Now I want to show one more thing, which is NIST Janus thermochemical table. So what is the use of this table? Using this table, you can find the value of delta G H per atmosphere, which will be useful for determining the value of equilibrium constant. Here just you can write that some chemical formula and you will get the delta G equal to 1. Now we will see the one problem related to our theory. In the dissociation reaction, O2 plus N gives 2O plus N. The change in gift free energy at 1 atmosphere is given by often A, GO2 P equal to 1 plus 2GN P equal to 1 plus GO P equal to 1 whole square. Often B, 2GO P equal to 1 minus GO2 P equal to 1. Often C, GO2 P equal to 1 plus 2G P equal to 1 plus 2GO P equal to 1. Often D, GO2 P equal to 1 minus 2GO P equal to 1. How to solve it? So we know that delta G P equal to 1 is given by sigma I, nu I, Gi, Pi equal to 1. This is Gp equal to 1 for product minus Gp equal to 1 for reactant. Now we have one reaction which is O2 plus N and gives 2O plus N. What are the product? Product are O and N. So for O, this new O product will be 2 and new N for the product will be 1. New O2 for the reactant will be equal to minus 1 because it is reactant. And new N for reactant will be minus 1. So we substitute value of this in this equation. We get delta G P equal to 1 equal to nu O P GO P equal to 1 plus nu N P GN P equal to 1 plus nu O2 reactant GO2 P equal to 1 plus nu N reactant GN P equal to 1. You substitute all these values here in the equation. You will get 2GO P equal to 1 plus 1GN P equal to 1 minus 1GO2 P equal to 1 minus 1GN P equal to 1. Here these two terms are same, so we will cancel out. We will get 2GO P equal to 1 minus GO2 P equal to 1. So correct answer is option B, which is 2GO P equal to 1 minus GO2 P equal to 1. In the law of mass action, Kp equal to pi I Pi nu I, where Pi is the partial pressure of a species I and Bi nu I is the stoichiometric number of a species I. Positive for products and negative for reactants. The following statements is or are true. Kp is the function of temperature. Kp is function of both pressure and temperature. Kp is function of pressure, temperature and time. Kp is defined as equilibrium constant. Often D you can directly say that true because Kp is truly defined as equilibrium constant. We have derived it some time ago. Now we have to find that on which properties the Kp depends. So therefore we have derived that pi I Pi nu I equal to e to the power minus delta G equal to 1 upon R1 T, which is equal to Kp. Now if you see this part, you can see that Kp is function of temperature only. So the option A is also correct. Kp is the function of temperature. Now we'll see the next problem. It is very straightforward problem. In the dissociation reaction, 1 upon 2 O2 tends to O, the equilibrium constant is expressed as option A PO2 upon under root PO, option B PO upon under root PO2, option C T2PO upon PO2, option D PO2 upon 2PO2. So how to find Kp, equilibrium constant? This is given by nothing but pi I pi mu. So we have to find first this mu. Now our reaction is half O2 O. So mu O will be equal to 1 and mu O2 will be equal to minus 1 by 2. So we put all this value here, which will give pi PO mu O into PO2 mu O2. PO to the power mu. Now if you substitute value of mu O and mu O2, we get Kp equal to PO to the power 1 and PO to the power minus 1 upon 2, which will be equal to PO upon under root PO2, which is equal to option B. Now we will see one more derivation, which is for want of equation, which is given by, so I will read the problem. Derive the following relation between equilibrium constant and the heat of reaction. D log Kp upon dt equal to delta Hr upon Rt square. This equation is called one-half equation. So how to derive it? First we have to know what is delta Hr. Delta Hr is nothing but enthalpy of product minus enthalpy of reactants. What is the enthalpy of product? It is nothing but mu I Hi. Enthalpy of product minus enthalpy of reactant is nothing but sigma I mu I Hi, because Hi is the enthalpy for a species I, so its difference will be the difference between the product and reactant will be the delta Hr. Now we will start with left hand side. So we know that Kp is pi I pi mu I equal to e to the power minus delta G equal to 1 upon R1T. Let's take a log of both sides. We will get log Kp equal to minus delta G equal to 1 upon R1T. And how is this delta G equal to 1 given by? It is nothing but sigma mu I Gi equal to, which is equal to minus sigma mu I Gi Pi equal to 1 upon R1T. Now in this equation there is derivative with temperature is taken. We will take its derivative with respect to temperature. So if we take its derivative with respect to temperature, it will, this nu I is constant. So derivative will be for this T and this Gi Pi equal to 1. So if we take for this T, it will become sigma nu I Gi Pi equal to 1 upon R bar T square. And for the second term, it will equal to minus 1 upon RT, sigma nu I dou Gi Pi equal to 1 upon dou T. So it is direct, it is ordinary differentiation, so it is directly D. Let's give it the name A. Now we have to find this dGi Pi equal to 1 upon dt. So we know this equation T dSi equal to dHi minus Vi bar dPi, which we derive from the definition of H, enthalpy. There is also another equation which is given by dGi equal to dHi minus T dSi minus S dt. Here this dHi minus T dSi, from these two we can get Vi bar dPi minus Si dt. So if we take Pi equal to 1, this dPi will equal to 0. So dGi Pi equal to 1 equal to minus Si dt, which is only function of time, temperature only. So if we take its derivative, we will get minus Si. So dGi Pi equal to 1 equal to dt equal to minus Si. Now we will put this value of this dGi upon dt Pi equal to 1 in this equation. Equation A. So d log Kp upon dt will be equal to, here we will take R bar T square as constant. We will get 1 upon R bar T square sigma nu I Gi Pi equal to 1. Here if you put this dGi Pi equal to 1 upon dt, it will become sigma nu I Si, and there will be negative sign. So this negative will become plus. So it will be T, we have multiplied T because we have taken common 1 upon R bar T. So it will be T sigma nu I Si. Now these both are summation. So we can also write this as 1 upon R bar T square sigma nu I bracket Gi Pi equal to 1 plus T Si. Now we know that this gi pi equal to 1 plus t si equal to hi. So we will put this here, hi here. So we'll get d log kp upon dt equal to 1 upon r by t square sigma dy hi. And we know that what is sigma dy hi? It is nothing but delta hr. So we'll get d log kp upon dt equal to 1 upon r by t square delta hr. So this is how we put this relation. There is one thing which is that I have simplified some step before, like here. Here I directly put this fi here, but before it was like this. If we put value of this as minus si, it will become d log kp upon dt equal to 1 upon r by t square sigma I mu I gi equal to gi pi equal to 1 minus 1 upon r by t sigma mu I minus fi. Let's take this common 1 upon r by t square, so we get 1 upon r by t square bracket sigma I mu I gi pi equal to 1 plus t sigma mu I si. Now this t will multiply inside, so we'll get 1 upon r by t square sigma I mu I gi pi equal to 1 plus sigma I mu I t fi. Now if both are in summation with the same limit, we can write 1 upon r by t square sigma I mu I gi pi equal to 1 plus mu I dx. Then you can see that here we have taken this mu I common and we got this derivation. Now let's check entropy. So for the equilibrium flow, this T dsi equal to del Q reversible, which is equal to dhi minus v bar I dpi. This is not the definition. So you can see that dsi equal to dhi upon t minus vi upon bar upon t dpi. Yes, minus it as equation b. Now we know that dhi equal to cpi dt, and cpi is function of temperature, and pi vi bar equal to r by t. So vi bar upon t will be equal to r1 upon pi. These two things we substitute here. So from equation b we will get dsi equal to cpi dt upon t minus r bar dpi upon pl, which is equal to integration si reference to si dsi equal to integration t reference to t cpi dt upon t minus r bar integration t reference to pi dpi pl. So if we integrate it, it will become fi minus fi reference equal to integration t reference to t cpi dt upon t minus r bar log pi upon p reference. Integration of 1 upon pi dpi equal to log pi, and if you put the limit we will get this. Similarly, integration of dt upon t we are not doing because the CPIs are the function of input. So SI will be equal to integration t reference to t CPI dt upon t minus r bar log pi upon p reference plus fi reference. Now this is for one species. If for all species we have to find the entropy, then we have to take the summation of SI. Which will determine what kind of species are there. So one more thing, that all the lectures which I have taken, most of the things I have taken from the book Hypersonic and High Temperature Gas Language by J.D. Anderson. And most of the things related to the course you can find in this book only. And so beside the lecture, if you want to follow some book, I think it is a good book to follow.